Good day to you. This is Galactic bringing you another science presentation in a series on geometry. This is not geometry such as you and I were taught it in school, although it is geometry. What we were taught in school was a specific kind of geometry, which is very interesting in that it's the only geometry we've ever used. Linear geometry. Linear geometry and linear numbers and linear algebra are all part of the same thing. They're part of the line, the linear system of representing universal space. The geometry that we will be talking about tonight extends that. It's an extension of the number system, although it doesn't change the number system itself. That was tried with complex numbers, and this new number system is similar to complex numbers, except they're not complex. They're called fractions. And those are two-component numbers. Every fraction has two numbers in it, correct? 1/2 has a 1 in the numerator and a 2 in the denominator, correct? Good. That's a two-component number, correct? Yes. But we can also say that it's just a linear number. It is representative of a linear number, but it's only representative of a linear number. A fraction, you would have to say, is not a linear number for at least one reason. A linear number has only one number in it. A linear number is called a one-component number. That's very important to grasp that fully. Is there such a thing as a two-component number? Yes. Can a two-component number be a linear number? Yes. If you want it to, you can reduce it. And if it's 3/1, you can reduce it to 3. And now it's not a two-component number. It's a one-component number. 3/1 is a two-component number. And you have to say that because that number can change when the 3 does not. So if you have 3/3, that's 1, correct? Those are two-component numbers. They're called fractions. When the component numbers of a two-component number, being a fraction, yes, when those two numbers are whole numbers, then it's called something else. It's more than just a fraction if they're whole numbers. The idea of a fraction, according to what we were taught in school, is you can have any number which would be a real number ordinarily. A real number which is supposed to be a representation of a continuous line number. It's not, but it's close. In a sense, it's close. When you use calculus, you can make it as close as you want. The reason you have to do that is because, for instance, you can have, and by the way, the name of that kind of number, when it's a fraction, that's a two-component number that can be reduced to a regular one-component number, and that's a linear number. 1/2 can be pinpointed on the line, correct? Yes, if it's 1/2, it can be pinpointed on the line. What about 1/7? Can you pinpoint that on the line? No. Actually, you can't pinpoint 1/3. You can pinpoint 1/2. You can reduce it to what's called a decimal fraction, or a decimal representation number. That's one number, but it's considered now to be real. And so 1/2 is exactly 0.5. And that's not a two-component number. That's a one-component number. A one-component number is called a linear number. And now the question is a fraction number a linear number? We were taught in school that it is. I'm telling you, because I've proved this, no, it's not. 1 over 2 is not a linear number. It's a two-component number. And a two-component number cannot be linear. It can be linearized. It can be turned into a linear number, but now you have to define what is the domain of that kind of linear number. And now you've lost everything. Because 1 over 2 can be represented as a linear number, but 1 over 3 cannot. And no computer can represent 1/3 because it has a repeating decimal. It's 0.333 ... And that means that 3 repeats to infinity. To infinity. And so now you have infinity in your number system. That is a problem. And here's why. If you just use whole counting numbers, what you get is half of a line. And there is no 0. There's no number 0. But if you're measuring linear separation, you have to have a 0, or you can't get to 1 from anywhere, because it would be coming from infinity, because the line goes infinitely in the other direction. That's called the plus-minus valence of the straight line. That once you have a center point to the line, your measurement of linear separation is strictly with the positive numbers. Strictly with the positive numbers. But the smallest distance that you can measure is 1. And in order to do that, to measure a distance of 1, you can put 1 at one end of the line segment. But then you need another number, or that 1 has no meaning. That 1 basically would not end at 0, or as you could say, begin at 0. Instead, that 1 would represent everything on that side. I'm sorry, the 1 would be everything up to 1 from the other direction. Well, that's not 0, that's infinity. So you've chosen to make a 1 to make your measurement, but you have no 0 to cut off the line in the other direction. Therefore, you have no measurement, unless you have 0. And that's where we get 0 from. 0 is the replacement for infinity. It's either 0 or it's infinity. And if you try to get around that by measuring from -1 to +1, you think you're getting around 0? You're not. You're going right through it. And so you can't get rid of 0. It's the center of the system. It's the center of what system? It's the center of the linear system. It's the center of the linear indexing system. And the index is 1, because that's the shortest distance you can measure. We're saying so. This is, you may recognize this from previous lectures, this is the antipodal theorem going to the bootstrap theorem. This is to kickstart mathematics geometrically. We can do that now through the work of several geniuses in the 20th century, culminating in the work of John Horton Conway. who finally got a definition of the number from which I got the definition of the line. And therefore what I say about the number 0 is based on proven axiomatic steps in a Euclidean proof sequence, which you're now going to hear again in order to introduce this man over here, Christiaan Huygens, which I'm going to try to say in Dutch, but it's very difficult to do. In English, if you want to say it as closely as I think an American can manage without losing his mind, it's Christiaan Huygens. It's Christiaan Huygens. It's kind of like Huggins, but it's it's and then the G, I can't pronounce it. And then the E is a schwa, and it's uns. So it's Huygens. And the G I'm not even going to try to say, although we're going to listen to something in a second, so you'll know how to say this man's name. Who is he? Maybe you've never heard of Christiaan Huygens. He discovered the spherical nature of light propagation, and he's given credit for that before Maxwell, and that's true. Christiaan got it before James Clerk did. James Clerk did not get it first. And we're finding that out in some other areas too, like Bošković discovered the quantum. It wasn't Bohr, it wasn't Einstein, and it really wasn't even Planck. It was Bošković who got it, and he got more than that. He got the geometry. So did Christiaan Huygens, which is why you're seeing him there. To complete our brief journey into the bracketing information for what we're doing tonight, the flight of the photon, we're trying to get a definition of the universe. We need a working definition of the universe, and in order to get that, we had to first crack the nut of infinity. So I'm going to sew that together for you one more time, so at least you have that as we get into the flight of the photon, which is the touchstone. Whoever can explain the flight of the photon understands quantum mechanics well enough to teach it to children. I currently believe I'm the only man who is capable of doing that. And as for children who have PhDs, you're included. I'll be teaching you as well. And don't worry about it coming from me. I'm not in the industry. I am not funded. I don't have any accreditation, no degrees. There's no reason you need to believe me. And I assume that you won't. But I still have to do what I have to do in science, which is to give you the truth about the propagation of light in free space. I know how to describe it geometrically because I studied the work of Christiaan Huygens and read his book, the same way that I studied the work of Bošković and read his book. So I know what these men say. And I can tell you that Christiaan got the propagation of light in space virtually correctly. And then everything that he discovered was forgotten in astrophysics and quantum mechanics. But it was not forgotten in optics. And opticians, optometrists, ophthalmologists, anyone dealing with human vision, anyone dealing with lenses, anyone dealing with microscopes or telescopes, anyone dealing with light knows that it propagates spherically. And yet we always measure it linearly. We have to. We only have linear numbers. I actually have something to offer to that called spherical numbers. They're similar to complex numbers in one sense. They're two-component numbers. And the first two-component number that you need to know about, I've already taught to you, it's called a fraction. And you may not yet realize, if you haven't heard my prior lectures, why that is so significant, that every fraction is a proportional number, a two-component number that's not complex. It doesn't have an imaginary component. That's the failing of complex numbers. There's an advantage to complex numbers in using an imaginary component. It's very familiar. It's used as a shortcut in upper-level physical mathematics. They all use complex numbers, and that's the only kind of number that's used in physics. is complex numbers. You can check. The Einstein field equation is written in complex numbers. The Dirac equation is written in complex numbers. The Schrödinger equations are written in complex numbers. Complex numbers define the sphere. For anyone dealing with spherical space is called the Riemann sphere. Look it up. It's exclusively complex numbers. So two-component numbers have proven their worth. But complex numbers are out the door. What we want is the good part, the two-componency. We already use it in fractions. 2 over 1 is not the same as 2. I just taught you the difference, so let's make sure we understand that. 2 over 1 is a two-component number whose linearized value is 2. And that becomes critical when you switch to 1 over 2. 1 over 2 is a two-component number that can be linearized to 0.5 in the decimal system, correct? What about 1 over 7? That cannot be linearized. And therefore 1 over 7 is not a linear number. And that's a fact. That is absolutely correct. 1 over 7 is not a linear number. Now, the reason that's important is to give you a taste of a two-component number. What is 1 over 7? Is it a linear number? No. Is it a one-component number? No. Is it a rational number? No! Yes, it is a rational number. And the reason it's a rational number is because you do not want to linearize it. If you try to linearize 1 over 7, you get an irrational linear number. It's 0.142857, 142857, 142857 to infinity 142857. That's called a period 6 repeating decimal. It is irrational. Because you can't draw a point on the line to make it. So it is not a measurable number, and it does not represent a measurement on the line. You got your measurement when you went from 0 to 1. Your only valid operator now is add. And I proved that fact. And I'll direct you to previous lectures, but I should be able to summarize it, but I can't go into that great detail now. Because we're getting to the flight of the photon, which I've promised 4 times over the past 2 months. I keep telling you I'm going to give you another tour of the universe, only this time we're going to be riding along with the photon as it traverses space from a star 1 billion light years away to your eye, right into your brain from that atom in a distant star. That photon has been proved to have gone in a direct straight line from that atom to whatever atom in your retina picked it up. A direct line from one atom to another at a distance of 10, well, I'll just say 1 billion light years. A directly straight line. Well, that's quite a little trip, isn't it, for a little photon to take that hit you exactly in the eye. The level of accuracy needed for that photon to go directly from the atom in that star to your eyeball, to your pupil, and go into your eye, the odds of that being an exact straight trajectory is flat impossible. Only using linear geometry, though. In other words, linear geometry does not explain the flight of the photon. It's absolutely impossible, and that's called the wave-particle duality. The reason why that's the same thing as the wave-particle duality is because when the photon arrives, it induces the collapse of a spherical function. That's called the collapse of the wave function. That wave that went out from that atom and that star is spherical. And that's what Christiaan Huygens proved. So let's take a look at Christiaan here so we have an idea of how he contributed to science. There he is, and this is from Britannica Encyclopedia. The Encyclopedia Britannica has some. This is a pretty good portrait. If you would like to get some other portraits of Christiaan Huygens, you can find them. But I thought this is representative enough, and there's some very good information. It's a very good article. He was, just to sum it up, a man who was born in 1629 in the Netherlands, and he died at a fairly good age in 1695. So his life overlaps with that of Newton's life and the life of Leibniz, but does not quite reach to when Bošković was born. So Christiaan Huygens lived before Bošković. He was a Dutch mathematician, astronomer, and physicist who founded the wave theory of light. That's correct. Were you taught that? Maybe yes, maybe no. I was not taught that. I was taught that Maxwell discovered the wave theory of light. It was actually Huygens. And he also discovered the true shape of the rings of Saturn. He was a very good astronomer, and he made original contributions to the science of dynamics, same as Bošković would. And Bošković, of course, knew everything that Huygens knew. Bošković knew everything that Huygens had ever known. And it's Bošković who figured out the force curve of universal space that explains the quantum paradox 100%. We're getting to that through the flight of the photon, but there's Christiaan for you. Down here's some more information. We're not going to read all this, but you can go to the Encyclopedia Britannica and read the article on Huygens. All right, so there we have that. Now here are some of his diagrams. Now I want you to see this one. I'm going to expand this so you can see that. If I can get the mouse to do what I want there. Let's see what this looks like. You can see there are a lot of circles being drawn in this diagram. These represent spheres. We have an innate problem with spheres. We have to project it down to a 2D image in order to really see it, and that's what's being done here. But these are spheres propagating through space. And you can see, I'm pretty sure you can figure this out. If I got an idea from looking at this, I think you will too. A picture is worth 1,000 words. It was never more true than here. In the first part of this, you'll see vertical red lines and then pink spheres that are centered on those points on one of the red lines. So that shows a plane wavefront. The second one, drawn in blue curved lines, is a different kind of wavefront called a spherical wavefront. And there you have it. That is the difference between the particle and the wavefront. Because when you measure a plane wavefront, you measure it as a series of particles, but when you measure it as a spherical wavefront, you can't measure it at all. And then the third diagram shows more information that's very, very informative on the difference between linear measurement and spherical measurement. We are extremely bad at making spherical measurements, and we've practically killed ourselves as a race trying to use linear geometry to compute spherical phenomena. And where it breaks completely is at the edge of space, because that's a sphere, and we can't compute it. And it breaks again at the inner limit, the inner, what's called the atom, which we now think is the proton, which we surmise is a quark. But we've never found the center of anything. We did, yes, Boshkovich did, and I did too. The center of any dynamic system does not exist physically. There is no physical center. You can imagine that you're seeing it by drawing any kind of geometric diagram, which is going to have a center to the spherical system. That center is not a point. It has a radius. The inner surface of the dynamism that we call the universe is not a zero. And that is called the quantum paradox. Here, just to have a little refresher, you may want to get up and make some tea or pour yourself a beer or whatever you like. Take a little refresher here as I just show you some interacting galaxies. These are called interactors or interacting galaxies. Here's a good shot of a few. This is the Wikipedia article on that, interacting galaxies. Here are some good shots of what they might look like if you were to find one. There's a good one. Look at that. That's two galaxies. Look at what they're doing. You ever seen anything like that? That's called the mice. These are two galaxies that appear in Halton Christian Arp's immortal, monumental book that changed the lives of a whole generation of astronomers. Arp's peculiar galaxies. Most of those peculiar galaxies are kind of like this. They're interacting galaxies. Pretty impressive stuff, I would have to say. All right, so there's enough of our interacting galaxies. We've paid a visit to Christiaan Huygens. What do interacting galaxies have to do with anything? Do you know what's causing them to make these strange shapes? Obviously, when they get close to each other, they distort each other. But is that gravity causing that? The standard cosmological model says yes. I urge you to reconsider what they say. Are these galaxies interacting gravitationally? Gravitationally. The standard cosmological model says yes, and there is no other answer. But isn't the whole universe composed of electrodynamic phenomena? Certain theories have arisen over the past few decades suggesting that this is not gravity that's causing them to interact in this way. And I wish I could show you a gallery of interacting galaxies where by the end of that expose, with me just kind of giving you some clues as to what you're seeing, you're going to realize that it's not gravity that's causing the interaction. It's electrodynamic force relation. And that's what makes them distort. All right, so much for that. I hope you enjoyed that little brief intermission. And now we're going to engage the flight of the photon. What happens when light propagates through empty space? Now, if you know something on this subject, I suggest you forget whatever it is you know, and just consider what I'm saying for now, because I have a different approach, which I think you're going to find ultimately refreshing, explanatory, satisfying, and it might give you a thrill. If it does give you a thrill, it's because you are a real scientist. Because this is pretty intense. So let's try it. Let's see what we can come up with. The geometric flight of the photon. The first thing you have to know just so you have something to think about as we talk about this, is that a spherical wavefront is exactly what that says. It's a sphere. And so what is a photon? The first word that should jump into your mind, it's a sphere. What kind of a sphere is it? It is the strangest sphere you've ever heard of, but it is a sphere. You must bear that in mind. Christiaan Huygens proved it. It is accepted in physics. There's no reason to question that. A photon, when it's traversing free space, does not do so as a particle. It does so as an expanding sphere. And that is the quantum paradox itself, because that thing that we call a photon, which is a sphere, which eventually has a radius of 1,000,000 light years, if that star is 1,000,000 light years away, then the radius of the sphere of that photon, the radius of that sphere is 1,000,000 light years. And you may recognize the rudiments of entanglement right there, and superposition right there, and the measurement problem right there. But what it really shows most clearly to, I think, all of us who know anything about quantum mechanics and what the fuck is the paradox, it's that that sphere simply cannot exist. And yet we know it does. And so that is the strangest sphere that has ever been measured. And that produces the measurement problem. Now I've named at least 4 aspects of the quantum paradox, but the biggest one of all is the collapse of the wave function. Do you know what that means? That means that, for instance, a 1,000,000 radius sphere, whose volume is inconceivably big, that is a bubble that we call a particle, but it's actually a sphere. It's not a particle when it's in space. It's not a particle. It's a sphere. But when it reaches its objective, which would be your eye, that sphere disappears in no time at all. It disappears without transitioning. It disappears without any space or time being involved. In other words, it goes back to being what it was when it left the star's atom. When that photon began its traverse of free space, it was a particle at the moment it departed, but that's an immeasurable moment. It detached without traversing space or time. That's a fact. It's called the quantum jump. It went from the surface of the electronic shell and detached in no time and assumed a new shell that has no space involved. So it jumped out of the atom without using up any time and without covering any space, and that just appears in another place, but with no distance in between that was actually traversed. It jumped over the space, and then it jumps again, and it keeps jumping. It's quantized. That's what it means. It's a quantum particle. And so it travels as an expanding sphere. Through what? Through space-time. And when it arrives as this gigantic sphere, the bubble pops in no time at all, and it reverses what it did at the surface of the electronic shell from which it departed 1,000,000 light years away. It simply reverses its impossible jump and jumps into your eye. And the rest of the sphere disappears, and that completes the flight of the photon. The question is, how in the world did that sphere collapse when a Planck unit of time before it reaches the surface of your eye to involve itself with an atomic system again for the first time in a million years? It simply does so as if nothing had happened, and we measure that as a straight line. But it's not a straight line. But it is. But it's not. But it is. But it's not. That is called a paradox. And the Boschkovich curve demonstrates why you're having this nightmare. You have to see it, or you cannot be cured of it. Your mathematics will not tell you this, although mathematics perfectly supports it. That's the mathematics that I'm going to be teaching you from now until the equinox. The mathematics of electromagnetic propagation. In order to get a definition of the edge of the universe. And you may say, you may think, I would, right offhand, if I didn't know what I was about to say. You certainly don't. Oh, unless you've heard my previous lectures, in which case you already know all this. Well, my job is to tell it to you again, not to tell you to listen to my previous lectures. The way we can get a definition of the edge of the universe, that every child wants the answer to that, and nobody can answer their question. Well, then you're not a very good astronomer. If you can't even answer a simple question from a child on what is the edge of the universe, then you're really not worth your weight in shit, are you? That's why you're listening to me. You would like to be worth your weight in gold, perhaps, to other humans. That's how you do it. You learn the truth from the universe, not from me. Definitely not from theoretical cosmologists and modelers who are lost in a world that they can't get out of. You can get out of it, though, but you're going to have to try. So, the flight of the photon cannot be explained. It's never been explained. But we do have two working explanations of sort for the flight of the photon. One is, we can measure the time that it takes if we know the distance. And we can measure the distance that it covers if we know how long ago it was, because the speed of light is constant. And so if you know the distance, you know the amount of time. That's called a light year, is the standard metric for that sort of a unit. But it's a speed, it's a two-component number. It's a relationship between distance and time. It's a fraction. The question is that fraction a rational number? That's why I introduced this with a little bit about number theory in the best sense, not guessing, but what numbers actually are and what they do for us. You can use a linear number, which is a one-component number, and what can you use it for? You can use it to measure distance on a line. That's a one-component number. What about the flight of the photon, which does not fly through space on a straight line? Well, you just pretend that it does, because the speed of light is constant. And therefore, you can get a linear distance fix on that star just by looking at its light. That's where it is. That's relativistic. That's where it is at the moment that you see the light. Now, in its local time frame, it could be somewhere, you might say it's not really there. That's not how we see. Yes, it is really there. And everything else you say is nonsense. Yes, it is really there. And how you explain the fact that it's continued to move while the light is traveling, that's up to you. Good luck. I already know how to explain it, but I know that you don't. I'm trying to get you to see the paradox so that you'll appreciate the answer, because it's highly explanatory. That photon can be said to travel on a straight line as a particle from atom to atom. That's what it is. It goes from one electronic orbit as an emission particle, and it is absorbed as an absorption particle. That would be your eye or the plate, whatever you're capturing that light on. Preferably your eye would be best. But with photography, you can see more. You're not looking directly at the object, but your camera did, and it just keeps absorbing photons. You have to track, because the Earth is revolving underneath the telescope. But if you track it right with electronic equipment, you can track that long enough to get way more many photons, fill up an image, and see it like you cannot see it with your naked eye. That's the miracle of light. It's magic. It's unbelievable that we can see that far, and still, by the use of lensing and just technology, we can actually get an accurate picture of that galaxy. To a threshold, it's always to a limit, but we certainly have seen way farther over the past century than we were able to do in 2,000 years before that. And that's putting it mildly. This is really quite exciting. It should be very exciting. Everybody who's into science should be fascinated with this, so that they miss work and lose their jobs, and then they have to become scientists. But that's not how it works in this world. We don't have time, but that's what I'm here for, is so that you do have time. Because if someone explains it to you rationally, so that you can see it, know it, and prove it yourself, so you can fully understand it and have that eureka moment, that's what it's all about. But that's up to you. I can't force you to understand, and I could be a good teacher, bad teacher, good information, bad information, good logic, bad logic, good presentation, not so good presentation, lots of factors. But the basic rationale, the pure logic, the support, the truth about the flight of the photon, you can see it. I'm going to show you how to see it, but there will be a moment when you're going to have a certain reaction. You must expect this. I'm just warning you ahead of time that the paradox has been impenetrable for a reason, so the solution to it is going to be anti-paradoxical. In order for you to see through the paradox, so it's no longer paradoxical, and we do have a definition of whatever we're trying to get, the edge of the universe or the flight of the photon, just explain what's going on. If you're going to do that, only the phenomenon is paradoxical, it means you can't even define what you're talking about. So you're going to suddenly have a definition you did not have before. The definition, in this case of what is called a photon, is that thing named correctly. Is it a particle? Is that gigantic sphere, which it is? Christian proved it, and we have no reason to doubt. It's very well known. Light propagates spherically. 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 That means every photon is a sphere. Expanding. They all are expanding spheres. Every photon is. And they are quantized. So there is such a thing as a unit. And that's called the quantum of energy. And a photon, so called, as if it were a particle, is a quantum of energy. But what it's doing is it's traveling, isn't it? It's traveling at a known speed. That's very difficult to wrap the mind around. Why is it traveling at that speed? What caused it to travel at that speed? What is the impetus force that would give it that speed? We call it light speed. That means it has velocity. That means it has an energy component that's linearized. When that packet of information arrives, it's the same frequency as when it left. Actually, not quite. It shifted on its way. It shifted frequency. We know that is the redshift, and that's where we get the Big Bang. It's only from that piece of information that the light packet that traversed that huge distance, the absorption lines that are embedded in the continuous spectrum behind it have shifted. They actually shift to the left. It's the background that shifts to the right with respect to the absorption lines. And forgive me if I have that backwards, but you can see it's a relativistic shift between the background continuous spectrum, which is a color band essentially. That's uniform. It's just what light is. But the absorption lines have shifted with respect to the background color band. Why did they shift? That is, and we interpret that not that the lines moved. The lines actually stayed where they were. But the entire frequency band shifted. It's a real question then, did it lose energy? If it shifted down, did it lose energy? Well, yes, it did. It lost some energy. How? How did it lose energy? It didn't lose enough energy so that we would not see it. But actually, if it's far enough away, you can't see it at all, but it would be very far away if you could not see it at all. Because that would mean that all the frequencies had shifted down and collapsed at zero. So whatever energy band, well, actually it's an energy packet, it's a specific frequency that so-called photon is. It goes out as a sphere, and it keeps going, but when it reaches its objective, it collapses back into a particle in no time at all. That requires some kind of explanation. Einstein certainly thought it did. He hated that. That's what he fought against. It wasn't the fact that that's what was happening. It was the explanation for what was happening. And he claimed to his dying day that someday you're going to find an explanation for that. And then ever since then, this debate has raged over whether that day will ever come. And the Copenhagen theorem, which is now officially true, and Einstein is officially dead, well, of course he's not, but according to Stockholm he is, and 90% of all scientists today are glad that he's dead and gone, in terms of him haunting us with his goddamn kvetching about the fact of this collapse of the wave function. He didn't like spooky action at a distance. The thing cannot be entangled at a 2 billion light year diameter, that 2 billion light years away, that part of the sphere just suddenly collapses in no time at all. Well, I'm sorry, but you're going to have to come up with a parallel universe to explain that. Actually, that's almost exactly right. And there is a hidden universe. It's a mathematical universe, and it does exist, and it can be proved to exist, but until you see it in the right geometry, you simply can't see it. You'll always be measuring it, but your measurements will never make sense, and that's called the quantum paradox. So the flight of the photon teaches us a lot right away. Once you know about Christiaan Huygens and you know about James Clerk Maxwell, you know about the spherical propagation of light, that when that packet, that unit, it's a unit of frequency measured energy. Energy and frequency, Max Planck proved, you can measure them with the same unit. That frequency fully represents energy. Frequency equals energy on a conversion factor called a constant. That's the Planck constant. I made a tremendous study of this to get down to the absolute mathematics of this. And what it implies is that Einstein is correct. There is such a thing as time-space. That is, there is such a thing as space-time. And I've covered in the past the difference between space-time and time-space. The one we use, the one that all physics uses, exclusively, the only geometry left. This is the top. This is what science has achieved. According to science itself and the popular view, all the authorities, all the consensus, I'm totally on board with this. But we need to understand it now. What is space-time? That's what has been proved, is that space-time exists. Space-time. Space-time. They're not separate. They're one thing. Well, do they have a relationship? Does space have a relationship to time? Yes! They're the same. They're measured the same. Whenever you measure distance, you're measuring time. And whenever you measure the passage of time, there's some kind of change of position involved as well. In space-time, that's been diagrammed in space-time diagrams, but you don't want to look at those. You'll actually lose your mind if you try to understand it too long. Because it's linearized. Well, that's insane. It's spherical. The phenomenon is spherical. But you're measuring it with straight lines. Well, that leads to the collapse of the wave function. You're going to have to come up with something to explain both at the same time. You can't. Unless you listen to me. But it's not me, it's what the universe says. You don't use a one-component number. Obviously you can't. It's time-space. Well, it's two different data types. There's time and there's space. So if you're going to measure it, you're going to need a number for time and a number for space. Well, Albert Einstein showed us they're orthogonal. So now we know time is orthogonal to space. Well, you might ask why. Well, this might be the right time to say shut up and compute, but I would never say that. That's what David Merman said is the motto or pledge of allegiance of the Copenhagen theorem, which is really a theorem with the blinders on. They've chosen a side in the quantum paradox, and they want that one to be true. Well, you can't. It stays a paradox no matter how loud you shout. And just because Einstein is dead, well, Bohr is dead too. But the ideas fight on. Stockholm keeps... Everyone is given the prize to Bohr just to settle the matter and just sweep Einstein out of the way. He's a pain in the ass. He keeps saying, no, there has to be a hidden variable. So John Bell came along and said, I think I can devise an experiment where you can at least prove whether there's hidden variables describing the collapse of the wave function in spukhafte Fernwirkungen, which Einstein hated and had nightmares about until he died. I've inherited Einstein's nightmares, but I don't like nightmares. I like science and solutions. So we're coming up on 55 minutes. That's your introduction to the flight of the photon, but I want to give you a teaser for the next lecture that'll close this out, and then we're going to turn to spherical geometry and explore it. The number system, the geometry, the relationships, the metric, time, space, sphericity, the circle, the relationship between the sphere and the circle, the relationship between the sphere, the circle, and the straight line. We're going to get the point out of the way. We're going to start using the actual surface of the universe, not a point. That's been proved. It's a sphere, but what does that mean? That's where time is. Time is on the inner surface of the universe, to the same proportion that space is on the outer surface of the universe. Space bounds the universe, and time is at its center. That does not make sense until you realize it's a distributed center. Oh, really? And the edge isn't distributed. The edge is distributed in all directions. But the center is also distributed in the opposite direction. Where would that be? Wherever anything is spinning in. Where do you see things spinning in? The atom. The atom. Those electrons are being held to a pretty perfectly circular, actually spherical orbit. Why are they hanging out in spherical shells around the proton nucleus? Why do electrons do that? Why do they go to those shells and stay there? Why do they not go to any other positions? They always go to the same positions with respect to a nucleonic shell, a nucleonic core, called the nucleus, which can be as little as just one proton. For some reason, the neutron, electrons don't even care about it. I'd like to see if there's any research into firing electrons at neutrons and see what happens, but apparently electrons just don't care about neutrons. But they care a lot about protons. When an electron gets close enough to a proton, it snaps into a spherical orbit and won't go anywhere else. That's where electrons want to be. If they find a nice proton to match their so-called charge, then they go into a spherical orbit around it at a quantum shell and nowhere else. Another problem to add to the problem of why do the electrons pile up in these shells and then stop doing it at a certain limit. That's where we get the periodic table from. It's not infinite. You can only have so many protons crammed into the nucleus, and then it starts to fall apart by itself. So you can only get about 100. It's a little more, but uranium is atomic number 92. That's 92 protons. Well, that's why it fissions so easily. So there's a little thumbnail sketch of the atomic system. Those electrons are extremely peculiar in their behavior around protons. They make atoms. Well, we've been trained to, just take that for granted. Don't take that for granted. Those electrons are extraordinarily peculiar in their behavior around protons. They go into shells at fixed distance, and it's universal. But the proton is even more peculiar. Why? It's always at the center. The protons just occupy a center, but they do something. And the electrons show what the protons are doing. The electrons are going into spherical shells around a center force. So the proton is doing something to space. You could think of it that way. Maybe it is and maybe it's not. Maybe it's affecting the electron directly. But whatever is happening between that proton and electron, the electron is attracted towards the proton with an electromagnetic charge valence that attracts them. The electron starts heading right for the proton as if it were under the influence of gravity. But it won't hit it. As soon as it gets close enough, it changes domain and becomes a spherical shell, not a particle. That is very similar to the photon. Well, that should not surprise us. The photon is just a piece of an electronic shell. It's a little bud that popped off of one of the shells and went away. Why it goes out at that rate, nobody has explained. It's been standardized. The equivalent number is 300,000 kilometers per second. You could say 3 million meters per second, and you could make it exact. It has been made exact. 299,792,458 meters per second. Why? Why does it go at that speed and no other speed? There has to be an explanation for that. Nobody has ever tried to come up with an explanation For why it is that speed and not another? There has to be a consistent force that explains that, and I found out what it is. It is the reciprocal of the protonic force. The proton is basically bending space. And the electrons, when they get close to the space around a proton that's occupying a center of space and influencing what's around it, that's through space. That's called a force. We say that it's the plus charge force. It's indistinguishable from gravity. It's an attractive force. That's what gravity is. An attractive force. Well, for every action, you have to have an equal and opposite reaction. So that's what we see. And that is the spin component. That is the direction in which space travels. Space is being bent inward everywhere that there's a proton. Everywhere that a proton exists in the universe, space is bent. You can think of it that way. Einstein did. But then he went a step further and realized that time is involved. And so he involved it in an orthogonal relationship with space, whereby he linearized time, because space is already linearized, so we don't know how the fuck else to configure space. So it's always linear, and so he made time linear as well. Well, that leads to a nightmare called the Einstein field equation, which I studied and I mastered, so I can pass on to you what it means, but don't try to figure out what that means. I'll tell you what it means. It's a definition of gravity based on the linearization of time with already linearized space in 3 dimensions, making a 4-dimensional system, meaning a 4-component number. A 4-component number. Remember, spherical space is composed on a 2-component number. Linear space is composed on a 1-component number. Time space is composed on a 4-component number. Why? Because there are 3 dimensions to space, and Einstein added a 4th. When he did that, he turned space inside out, because this has to be imaginary. That means it has to be signed negative. Whereas the 3 positive axes of space are positive, because that's distance. Time is negative. Is it? Is time negative? No. What is it, though? There is a relationship between time and space that allowed this to work. It does work. It is a linearized solution. It's the linear solution of gravity. Extremely complex, extremely complicated, non-understandable. Why not? I said I understand it. I do. But you never will, and I'll tell you why. You could. But I want to save you the pain. Because this is what you're going to get. Instead of it being spherical, which it is, gravity is a spherical phenomenon. Everyone knows that. But we don't have spherical geometry. What do we have? Pseudo-hyperbolic. It's pseudo-hyperbolic. And hyperbolic means you take the sphere and you turn it inside out. Then you get a hyperbolic surface. This is well known, but why you would want a hyperbolic surface? Why would you want a hyperbolic surface? It's because you had to negate time to make it imaginary. That is the reason for hyperbolic space. But when you do that, you're now working on a 4-line system where you can only see 3 lines. There's an imaginary 4th that's orthogonal to all 3, if you can picture that. The only way that you can compute in that space is to do what Einstein did, with 2 catastrophic results. You get a hyperbolic geometry, which is not even that. It's not even hyperbolic geometry. It's pseudo-hyperbolic. Because how are you going to account for the curvature? When you have a 4-line grid where one of them is invisible, you still have no curvature anywhere. You know where the curvature comes in? 4 tensor calculus. And if that doesn't send a chill down your spine, it's because you don't know calculus well enough to appreciate that that cannot be computed by a human. It would take you decades or centuries, or you'd never get it. But with supercomputers, it can be done. And that's why your GPS works. And that's an hour and 5 minutes. I hope you've enjoyed this introduction to the flight of the photon. As a spherical surface, it's not linear. It's spherical throughout. It causes a paradox at the collapse of the sphere in no time at all, back to what it was when it left an atomic surface from an atomic shell in a distant star light years away. It traveled out as a sphere, got bigger and bigger and bigger, and then as soon as it got to your eye, that sphere just disappeared by magic and it turned back into a particle. And that's the quantum paradox. But at least you see why it's a paradox. And I'm going to tell you the solution in abstract mode so that the mathematics that I'm about to teach you over the upcoming weeks will make contextual sense. It's self-explanatory. None of it is difficult, but it uses a 2-component number, and apparently that just throws everyone off. I don't know why it would. We've been using complex numbers at the top level of physics for over 100 years. So why would complex numbers all of a sudden, be worthy of the fundamental theorem of algebra? The fundamental theorem of algebra says that complex numbers are God. That's what the fundamental theorem of algebra has come to be said to be. That is not true. You do not want complex numbers. What you do want is the power of a 2-component number, because one of those is going to be time and the other one is going to be space. But to understand the geometry of it, you're going to need 2 things. You're going to need my explanation of the Boschkovich force curve, and then you're going to need the geometry that I discovered in 2022. With a closed 2-number component system for a pure spherical space that completely describes space better than a 3D grid. Only it already has sphericity in it, so you don't need calculus, and it uses nothing but positive, rational numbers. And I hope that that helps. I know that it does, but I'm saying it that way so you will carry this forward. This is just the beginning. This is Anagalactic, broadcasting to you from Chico, California on the last day of March in 2023 with a brand new geometry that solves the quantum paradox. It will get us back to the Big Bang and solve the Big Bang paradox as well. We now have a full, complete definition of infinity that completely supersedes all others and erases the others. Cantor's work is erased, and everything anyone has ever said about infinity was for the playpen. I discovered infinity, and I discovered the quantum number system, and I discovered the geometry of the universe. And that's what we're going to be talking about until I drop dead. And if anyone listens, great. If no one listens, that's even better. Then my reward is not here at all. That's why I keep saying, if you've heard some of my past lectures, I very often say I don't care what you think or want or do. It's not true. Of course, I care about everyone. But in order to be of any benefit to you, I'm going to have to give you what you want. That's going to be partly up to you. If I give you what you want, and I give you the answers that you want, I don't care who you are. If I give you the answer that you want and need, and you clout me for it until I'm dead, I would not be the first, but I'd rather stay out of your way. This is good for me. You don't necessarily need to know this. You may not want to understand the universe. You may not give a shit about truth. You may be doing what you want. You have no interest in truth. You don't care what happens to you after you die, and you're a meaningless little crud. Or you're one of my kind of guys. You're one of my kind of men or women. You want the truth. You're willing to trade anything for it. You don't care what comes, hell or high water. You want the answers. What is the universe? I know I can understand it. I want to understand it. I will teach you. We'll be right back. Stay tuned to Anagalactic.